Okay, I'm going to look at fluid statics from Chapter 7, and this is section 7.3. All right, so this is dealing with fluids at rest, as opposed to fluids in motion, which we'll look at a little later, fluid dynamics. With fluids at rest, we have the system will be in equilibrium. That means all the forces that are acting on the fluid are going to sum to zero. All right, so, and what we're talking about is vector sum, which means you have to include direction. All right, that's all part of it. So summation of all the forces, vector forces, is equal to zero. Okay, so first thing we're going to look at is pressure elevation relationship. All right, and what we have here is change in pressure is equal to the specific weight. And remember, specific weight is just the density times gravitational acceleration, which is, weight per unit volume, okay? And then times the height. And height is the elevation change, right? So h, or if you want to think about h or as height. But this is the elevation change between one position and another position in the fluid, okay? So if you go down in the fluid, this change is going to be positive. And if you go up in the fluid, essentially, you'll find this will be a negative, okay? So it decreases. Now, if we look at submerged surfaces in this case, the force on that submerged surface is essentially the pressure times the cross-sectional area. So if you had a surface that was a certain distance down in a fluid, you could calculate what its pressure is, which is something, pressure, of course, is always just force per unit area. And if you multiplied it times the area that you care about finding the total force acting on it, you would come up with the force, right? So you just multiply it times that area, and then you can come up with the total force acting on that surface, all right? Okay, now if it's a so-called partially submerged surface, now this might be like a face of a dam, all right, so part of it's underneath the water. If you wanted to find the force or the magnitude of the force, so if you took all the forces acting on, let's say, the surface of a dam, that's again holding back the water, you would have, specific weight times h times the area divided by 2, okay? So it's half of it, right? And if you look, essentially what we do, we just basically said, the area divided by 2 or the pressure over 2, right? So this was the pressure times the area divided by 2 will give you that, all right? Okay, so, partially submerged vertical surface. So here's an example. Here's a dam. Here's water being held back. And there's a couple of things here we're going to look at. The first is this force, right? And this is like average pressure times area. Okay, and this is the position down where this force is actually acting. So the average pressure is at some distance h down times rho, which is the density, times gravitational acceleration. Okay, so we're going to look at this in more detail. And this is in section 7.3, and there's 7.31 talks about this pressure versus elevation and forces on submerged surfaces, also in 241. So we'll take a look at some examples related to that, okay? All right, so that's it for this part. This is just the brief introduction. But there's a few things we're going to look at, and one is thinking about, yeah, you could take all of this water, figure out its pressure, and you can figure out the total force of the resultant force acting on the dam. So you could figure that out, which we recognize is just going to be half of the total, okay, of the lowest point, right? So it's like calculating's halfway, all right? And that was the previous calculation here. The resultant force is just that pressure times the area of the dam divided by 2. So this gives you the resultant force, okay? The second part we're going to look at is how do you calculate this h? Like where along this surface does this show up, okay? And we're just going to take a look at that, and it actually, what you'll find is it's just 2/3 of H being the whole height here. 2/3 of it. So it's like a third of the way up from here, or 2/3 from here. Now you could come up and derive that, okay, to find that so-called center of this pressure, which is, where that resultant force will be acting. For us, we'll just take that as it is, okay, without going through the derivation. All right, so it's going to be just the center of pressure. You can think about that is just 2/3 down for the top, and that's the way it'll always be in a flat surface like this. Okay.